It's great to be back in New York. The first year of grad school, this was my neighborhood. So if you need a watering hole, I suggest Waterfront Ale House, 2nd and 30th. Go there. Ale House. There we go. So when the Russians, well, back then the Soviets, launched Sputnik, it started the biggest investment in what we now call STEM. And the amount of science in the US went skywards like one of those Werner von Braun rockets, right? And, you know, nowadays satellites are part of our everyday life. And if you want to see how many of those are around, may I suggest going here. And you can see, like, you know, how many of those each country has. And you can make them dance. And you can see all these satellites flying around, and you can find out which what. So this is Hubble Space Telescope. These guys are going like crazy. They're military and spy, you know, keyhole satellites. And this busy strip here, it's all communication satellites, spying satellites. Then you have, you know, the positioning, GPS, and it goes all the way to the ones that are now circling around the moon. And when, you know, we speak about satellites, for regular users, they basically catch our eye and spark our imagination, right? So you see this one, and you say, screw my boss, screw polar vortex, I need a vacation somewhere warm, like blue seas, right? Or you see something like this, and you say, oh, reminds me of a wicked acid trip I had in college. And I should know a thing about acid, for one reason only. That's because I'm a chemist. Now, if you want to make acid in your kitchen, you need like 6 pounds of barley or rye. You need 6, you know, cookie trays, a humidifier. If you want to find out the rest, buy me beer and I'll tell you this treasured family recipe. My name is Milos. My last name is really hard to spell and pronounce by native English speakers, as we've seen from the previous talk. So I was born in that country, Yugoslavia. So now you know that I speak 5 languages. And my mom thinks I'm very smart. Now, why would you use Python scientific stack to analyze satellite images? Well, you know, it's free. We're all here for a reason. And Python has very rich, you know, ecosystem for, you know, GIS analysis. But most of those are basically bindings, you know, to C for all those things. And, you know, they're there for a reason. I mean, Python is nice, but all image analysis lends itself to being highly parallelized. You can now run it on GPUs. And in that respect, you know, Python is still way back, but, you know, it's free. And what's best, you can, you know, get satellite data for free nowadays. The biggest custodian of satellite data is US Geological Survey. And you can download data ranging back to 1920s, all the way to the latest satellite that, you know, they have in orbit that I'll briefly describe. Now, you know, dealing with this data, and it's usually, data set is around 1.7 gigabytes, so it's not easy to distribute. Also, you are not allowed to distribute yourself for people to analyze. So best way is you go to, you know, US Geological Survey, you register for free, and you can download what they call level 1 data. So that's basically very detailed data. That's, you know, you can download it while sitting on a couch, sipping coffee, and you can analyze it later using your, you know, Python scientific stack. So I'll be using Landsat 8 as our, you know, example satellite and data that was acquired by Landsat 8. It went up into the skies last summer. It is predicted to last about 5 years, and it will, you know, by its sheer number, it's 40 years of legacy for Landsat satellites. It's circling around Earth every 99 minutes. And it comes back to the same spot it took image from every 16 days. And its orbit is in such way, such angle and the height of orbiting, that it's what they call is heliosynchronous. So the orbit moves by the same angle as the Earth spins around the sun. So it's always at the same position and angle in respect to the sun. This is very important because you want to acquire your images at with same conditions. And to get those images, your rays of light have to go through the atmosphere. And now here in gray is where you have a window to acquire data, and in white is everywhere where atmosphere basically absorbs your light. So there's nothing coming through. And you can see the top row of bands is what is available with Landsat 8. And you can see that most of the time we are in the clear window, except this band here. And this one suspiciously is smack down in where the atmosphere strongly absorbs that, and it's there for a reason. So let's go ahead and start seeing what are all these bands that we have available. So band 1 is what they call coastal or aerosol. It's basically in little past blue, what you would call violet or UV. And it's there because this light, if you're scientific oriented, these are the wavelengths of the light. So, I mean, it's not really necessary for you to know. So with this, coastal line, you can see it's basically the same as the blue light, but it penetrates the water a bit deeper, and it's also scattered more by all the particles that are in the air, especially the water that's kind of atomized and floating in the air. So it's very important for the oceanic ecosystem. Now, the next three bands are what I'll be really used to analyzing it, red, green, and blue. So I'll come back to those a bit later. Then the next one is near infrared. So now this is getting into the area where people mostly are not used to this. So it's past, your RGB, what you know. But this band is important because it's very useful for analyzing plant life. Plant life scatters this light more effectively than anything else, and it's also telling you if the plants are alive or dead. So it's very useful for agricultural data. Now I'm doing this just to show you, how quickly or how easy it is to analyze this data in real time. And this is what you would expect. It's gray image. Now, I'll go back here to show you one thing that I told you about RGB. So here, I think I have an image of, it was called King Fire. It was fire that was burning, this is Lake Tahoe here. It was burning this, I think, August, one of the big fires. And you can see that, well, not really easily, but this is all the smoke coming out from fires. And what's good about having different bands for you to choose from is some of these bands can actually go through the smoke. So this is the same image. No, sorry. This is the different image. This is the image of LA, I think. Yes, this is the Malibu. So let's move to what I wanted to show you. So now we have the same image of that fire around Lake Tahoe, but you can see smoke is not visible there. It's because this particular band can penetrate the smoke. So it's really useful for basically seeing through what cannot be seen by naked eye. Band 8 is panchromatic, so it means the RGBs are collected at the same time but stored as a black and white gray image. And you can see now here that this band has the highest resolution of all bands. All previous ones were at 30 meters per pixel. This one is at 15. And it's really important when you want to analyze fine details in your image. Now, band 9, if you recall, it's that weird one that was sitting down where the atmosphere was absorbing. So why in the hell would, scientists put that band there? And it's for one reason only. It's for detecting, cirrus or cirrus clouds. These clouds are very high up. They're probably 30 kilometers up, and they're not clouds made out of gases. These are actually ice particles, and they're whiffy and thin, and it's really hard to spot them. And for precise measurements, you need really to know what is your light coming through and reflect it back to account for all these various things that can affect your precise measurements. And here, let's see. This is a snap taken over Paris. And you can see all the contrails from the busy airplane routes. And the contrails are also about the same height you would get them from the cirrus clouds. And this is making the scientists who analyze data their life very easy, well, or easier. Bands 10 and 11, there are, if you now recall back, the second group of bands in that image that I showed you, so they're part of a different instrument. All the bands up to this one, they come from OLI, which is Operational Land Imager, OLI. And now this comes from TIRS, which is Thermal Infrared System. Now here I'll show you bay in Nova Scotia, and unfortunately it's always a shame that the details get lost here, but this is the land, this is the ocean, and here you can see the currents which have different temperatures coming from all the glaciers melting and intermixing with warmer bay water. You also have another, if you go through all the process of downloading data, there is very important text file that you have there, and it has all the geodata, where it was collected, lat and longitude of corners and all that stuff. It has the readings from all the different pixels in your two images. This is also an advancement from previous satellites because this time data is acquired at 12-bit ADC rate. All the previous ones were at 8-bit, and the data is stored as 16-bit UINTs. And if you want to really drill into the data and analyze it in fine detail, you will have to look from time to time in this file, just write your routines to go pick up what you exactly need from that. And there's also another folder in that, another file, not folder, in that zipped file you download. It's band 11, it's quality band. And that quality band is very helpful because the data that you get is not really raw. It's already pre-processed by some stations that are taking care of that. And if I scroll further down, you'll see that as you read these, bytes from this quality band, you can already guess, or not guess, they tell you what was wrong with this, particular pixel that you're getting. So you can see that, if you get value 6, the first one, cloud, yes, no, snow, ice, and so on and so forth. And you can go to Mapbox blog. This is the company that is trying to commercialize all this data, and they have a great blog which is really down to earth. You don't have to be a scientist or an analyst to know what's going on there. So let's make our first image.
Can I ask you a question?
Yes?
Is there a way I could follow along with your Python notebooks on my own machine?
Yes, I haven't uploaded them all because, as you can see, nothing is annotated. So once it's annotated, go to my GitHub repos and it will be there.
That's the Hyperion, I know that it's one.
Yeah. And also for data, you have to register, download on your own because, yeah. So for this, I'll be using the, scikit image. That's all you need, plus Python. So let's start and see if this demo will go. So what I'm not trying, what I'm doing is just reading in the RGB bands that we, need for making pretty pictures. And while this is going on, if you want to analyze, in my experience, the best thing to do is do it on a Linux machine. It's the least trouble. OS, OXY, aka Yosemite is fine, but there is a little of hiccups because I think sklearn can have trouble reading the unsigned 16-bit integers. So you can change the plugin that's going on. It can complain because these TIFF images are geotiffs. They have all these geo tags included in regular TIFF files. But if you see all the warnings, don't worry about it. It will read in the image data, but the geodata will be discarded, which at this step we don't really care. And this is our, RGB image. And I was saying, what the hell is this? It's like completely dark. And the thing is, these instruments are calibrated to acquire data from really dark backgrounds. Oceans are, when look down from the skies, they're really dark. And they have to have a wide range. So from dark oceans all the way to, white snow caps on mountains. And for this, we need to, adjust our exposure. So this is basically stretching this range that was not used for acquiring image and kind of brightening our image first. So we'll do two things. We'll brighten our image and we'll adjust its contrast. And now you can see here, this is the distribution of our, RGB. And I intentionally, if you see here, I left out the first column because it's all the black pixels, which are those triangles. So they'll skew how your histogram looks. So this is your data, and you can see that only a small portion of what's available to you is being used for distributing this. So next thing we want to do is kind of stretch this across this axis. So we are utilizing the full width of range that we have at our disposal. Okay, now this is now looking up. Let's move further down, and I think here we'll plot how the new distribution looks like. And now you can see that, we've really stretched our pixels throughout the full range, and we probably overblew certain pixels because they go all the way up to 1. Now, this is kind of an iterative process. You go try one thing, it doesn't work, you move your limits left and right until you find the right range. And this is just a question of, experience and, trial and error. It's a valid scientific approach, right? So now that we've basically brightened our image, we need to adjust the contrast. And for this contrast adjustment, there's a range of functions. So we'll use a simple exponential function to adjust this contrast. And you can, play, again, it's playing around. And you don't have only the exponential function at your disposal. You can use sigmoidal functions. So in this case, you can choose, do I want to emphasize my highlights, my lowlights, or do you want to stretch your mid-range? So let's do this. Okay, now we have an image that looks pretty decent. Maybe, here certain things. Now, this is Guinea-Bissau. It's on the west coast of Africa. And here is the islands surrounding the river that's running. It's River Gebo, I think. And you can see that we probably, the river is not really wide. So those are the white pixels that we really blew out. And you can probably go back, but this is fun enough if you go and check out how image specialists are doing with the same image. You can see that they've done pretty much the same thing that we accomplished with a few IPython cell executions. Now at this point, if this luminary from History Channel comes up, I'll be talking aliens, right? Yes. When I say aliens, I mean crop circles. So these are actual crops in the form of circles, right? This is a shot of, I think it's in Kansas, like southwest of Dodge. And you can see all these bright circles. We use that, one particular band I told you that's really good at distinguishing the crops, the near infrared. And why are these perfect circles, or maybe like, oh, it's beer time. Why are they all there? I didn't know about that. It's called central pivot irrigation systems. And these systems, can make and grow crops around the year. And these things are big. Each of 4 of these circles is 1 mile square. And these guys are running this around the clock, basically. You can be growing crops, well, not really year-round, but stretch what would usually be a normal period of year to grow your crops. And this is also important because this is kind of the tail end of one of the biggest aquifers, Ogala aquifer, and that stretches all the way from, I think, North Dakota, all the way to Texas. And because of the advanced agriculture and, basically overusing our resources, certain parts of this aquifer are drying out. And it's very important to monitor this stuff because all this satellite imagery is being used for types of data that you may not really associate as like exciting. Like, I want to show people, what's going on. So agriculture, but everybody has to eat, right? Mining, we need all these metals because, believe it or not, one day we will run out of copper. Maybe, there's no copper, there's no, fancy Mac machines, to play around. We'll run out of oil. Oil industry is a big industry that uses this. What we will do then? And, at this point, as I was preparing this presentation, I think it was 5th hour of sitting in a bus somewhere between Boston and New York in a state which we call New York, Massachusetts. And I decided that, everybody has been at certain talk where people, show you the stuff that you've already seen or know how to do. And I want, for all you to leave out with one simple thing to know. So I decided to skip what I said in the abstract that I will show you. Like how to do little image recognition. So let's count all these circles, figure out what's the area, what's the yield of corn or whatnot. And then go back to that, triplet acid image. That's a copper mine in Arizona. And try to figure out, like, how long do we have to mine those minerals around. But, usually, we are kind of drawn to data that, has a story behind that. So, telling you about this is maybe not as good as telling you about, what was that study? Pornhub, why people in Kansas are weird in terms of use of the Pornhub website, right? So I want you to go out with one thing in mind, and this is in all this image analysis, sampling your data is really important. And when you sample your data, you can use maybe some sort of grid, but the grids are not good because they have some periodicity, and lots of signal processing is not really good for accounting for this periodicity. You can choose some sort of like random, picking of your pixels, but each randomness has certain things that are really not what you're looking for. So I went back, I remember, maybe it was this spring, I remember seeing there's this guy, Mike Bostock, he has a great website, and he had there this algorithm, which if you read the paper, you go, I think I kind of get it, what's going on there. But if you go to his website and have a look at how the algorithm is actually doing, it's great. So I want to show you, and also I thought that I'd be able to Google this. Somebody would have done this for Python because this is all for D3. Mike Bostock and Jason Davis, who came up with this algorithm, they have this available for D3, but not for Python. So, damn it, there's no copy and paste programming for me. But luckily enough, this is not such a complicated algorithm. So I'll quickly show you how the algorithm actually works. So as you can see here, we pick a point at random. Everything that's in the gray zone, it's an exclusion zone. You cannot pick another pixel that's in this gray zone. You can only pick a pixel that's in this circle here. Now, each pixel that you pick that's within this circle has to be a certain prescribed distance away from all other pixels. And now you do this, but by doing this, what you're doing is picking random pixels, but that are only a certain distance away. And you iterate this until you come back to each pixel, and once you come back for the second time to this pixel, you don't find available pixel for it, you mark it as black, as you can see here, and you never come back to it again. And this is all nice and fine, but let's see how it works for Python. So there you go, within like a second, we have this distribution, and as you can see here, it doesn't really look like random, but it's really random. Yes? Oh, 2 minutes. Okay. And why is this important? This image here is randomly picking pixels, and each of the area is encoded as color. And you can see here we have a huge variation in color, right? Randomly picking pixels. We use this algorithm. We have a really uniform distribution of area between the pixels. And this is done by constructing a Voronoi diagram. So I try to do that for it all looks nice and fine. But as you can see here, Voronoi diagrams unfortunately have those pixels at the edge that extend to infinity. And you cannot calculate the infinitely large area. So if we now just concentrate on really what's important here, we get what's really smooth and uniform. And now here I plotted the distribution of area. You can see most of those pixels are within a certain distribution, and all these pixels sticking out are those on the edges of the image, or so I thought. And let's see if I was right. So I only rearranged pixels here that they are sorted out. You can see most of them are really the same range, except that those that are really shooting up. Now, if I exclude those, high area pixels, you can really see that the troublemakers are the pixels that are on the outside edges, and everything else is fine. Now, this is where I stop, because I really haven't found a good way to include these pixels into the bigger picture. I think instead of using those faraway points as an endpoint of our infinite, Voronoi ridges, if I only limit them to what's, x and y limits of our image, I think this should be all nice and fine. And I plotted also the distribution of the included areas. You can see that it's fairly uniform. It works. I trust Mike Bostock because he's a really good guy. Right? So thank you for your attention. And if you have any questions, I'll gladly answer them.